So in this video we will look at alcohols. And alcohols are compounds where one or more of the hydrogen atoms in the alkane have been replaced by an OH group. So the general formula for alcohols is ROH, where R represents either a carbon or a methyl group. So how do we name alcohols? Well, like most other organic compounds, we first look at the number of carbons and then we use the prefix. So for one carbon it's meth, for two it's eth, two prop, and so on. And the ending to show that it's an alcohol, we use the ending of OL. So for example here we have one carbon, therefore it's meth, and because we have the OH group attached here, it's a methanol. So the same goes for ethanol. Again, as we have two carbon atoms here, the prefix will be eth, and because we have an OH group, the ending will be ol. Therefore, this is ethanol. And this example here, this is propanol, and it's called propanol because it has 3 carbon atoms and an OH group attached. We can also get more complicated alcohols. So for example, 2-methyl propan 1-ol. So first of all, we look at the name and we can see that it says propan. This means first of all that there are 3 carbons and there are no double bonds. So we can draw out a 3 carbons. We also have the ol, and the number 1 shows that the alcohol group, the OH group, is attached onto the first carbon. So we can put the OH group here. And it also says 2-methyl. It's saying that there is a methyl group on the second carbon. So the methyl group is attached to the second carbon. Also, ethane 1,2-diol. Again, we look at ethane, and it means that there are 2 carbons in the chain, and ane meaning that it's an alkane, therefore there are no double bonds, so we can draw 2 carbons. A diol means that there are 2 OH groups, and because it says 1,2, it means that each of the OH groups is attached on the first and on the second carbon. So we can represent ethane 1,2-diol as this. With diols you can also get triols, and triols are when you have 3 OH groups in a particular molecule. So let's consider the types of alcohols, and the class depends on how the OH group is positioned on the carbon chain. So there are 3 main types: primary, secondary, and tertiary alcohols. Primary alcohols are when the carbon which carries the OH group is only attached to one alkyl group. So for example here we can see that the OH group is attached to this carbon here, and this carbon here only has one methyl group attached. Therefore it's a primary alcohol. For example, propan 1-ol, we can see that the OH group is attached on the end, and the carbon that carries the OH group only has one other carbon attached to it. So again, it's a primary alcohol. 2-methyl propan 1-ol, again we can see that the OH is on the first carbon, and the carbon that carries the OH group is only attached to one other alkyl group, therefore it's a primary alcohol. Methanol is also primary, it's just one of those exceptions. Let's consider secondary alcohols. And secondary alcohols are when the carbon which carries the OH groups is joined directly to 2 alkyl groups. So the alkyl groups can be same or can be different. So for example, propan 2-ol, we can see that the OH group is attached to this carbon here, and the carbon that carries the OH group is also directly attached to 2 methyl groups. Therefore it's a secondary alcohol. Butan 2-ol, again, we can see the OH group is attached onto this carbon here, and this carbon here is attached again to two groups. Therefore, it's a secondary alcohol. And tertiary alcohols are when the carbon which carries the OH group is attached directly to three alkyl groups. So, for example, 2-methyl-propan-2-ol, we can see that the OH group is attached to the central carbon here, and there are three methyl groups also attached to that carbon. Therefore, it's a tertiary alcohol. Let's look at physical properties of alcohols. So here is a diagram which shows the boiling points of alcohols and compares them with alkanes that have the same number of carbons. So in this case, the first alcohol is methanol, and we also have methane. So the blue bars represent alcohols and the red ones represent alkanes. And as we can see from the trend here, that the boiling point of an alcohol is always much higher than that of an alkane with the same number of carbons. And this is because of hydrogen bonding. And hydrogen bonding happens between molecules where you have a hydrogen atom directly attached to one of the very electronegative elements, so fluorine, oxygen, or nitrogen. So here we have ethanol, and we can see a molecule of water. And because oxygen is very electronegative, it has a slight negative charge. So therefore the hydrogen is delta positive. And molecule of water, because of the arrangement and the bond angles, also produces this delta positive or delta negative. So the hydrogen on the water molecule will be attracted to the very negative oxygen, forming a hydrogen bond. Alkanes do not have hydrogen bonds. They only have van der Waals dispersion forces, and we know that hydrogen bonding is much stronger than van der Waals forces, which means that alcohols will always have higher boiling points than alkanes. So let's consider solubility of alcohols in water. So small alcohols are completely soluble in water, and this is because the OH bond is very polar due to the big difference in electronegativity. But as the length of the hydrocarbon chain increases, let's say we have 4 more carbons and beyond, the fall in solubility is noticeable, and you usually will have 2 layers in the test tube. So let's consider water and ethanol. And ethanol has only two carbons in the chain, so it's quite small. So the main intermolecular attraction when you mix water and ethanol will be hydrogen bonding. So first of all, you need to break the hydrogen bonds between ethanol molecules and water molecules as well. So and this requires energy. But when you mix water and ethanol, new hydrogen bonds will form between water and ethanol, and the energy released will compensate for the energy needed to break the bonds in the first place. So this diagram here, these red circles with the 2 white dots represent water molecules, and these represent ethanol. So as mentioned before, these are held together by hydrogen bonding. So first you'll need to break the bonds between the ethanol molecules and the hydrogen bonds between the water molecules. In order for them to mix, they will then form new hydrogen bonds between, as shown here, the water molecule and the ethanol. So large alcohols that have 5 or more carbons, they only have the OH group, which can form hydrogen bonds, and it's only at one end of the molecule. Therefore, the hydrocarbon tail can't form hydrogen bonds, which makes, and this explains why larger alcohols are insoluble in water. So let's discuss how alcohols are manufactured. There are 2 main ways of producing alcohols. The first one is called hydration of ethene, and we've discussed this in the alkene video. So in this case we have ethene with water at 300 degrees centigrade, the pressure of 600 atmospheres, with a catalyst producing ethanol, which is the alcohol. This is a reversible reaction because only about 5% of ethene is actually converted into ethanol. So in order to get a 95% conversion rate, the unreacted gases will be recycled back into the mixture. The other way is by fermentation, and fermentation is a natural process. So the sugar in the fruit ferments using yeast on the skin. It's quite a slow process, and the temperature needs to be around 25 degrees centigrade. So we can convert glucose to ethanol and carbon dioxide with the use of an enzyme in the yeast. So here we have a molecule of glucose with the presence of yeast, and about 37 degrees centigrade we get ethanol and carbon dioxide. However, there are some setbacks with this process. Is, for example, when the temperature goes above 37 degrees, the enzyme becomes denatured and fermentation will stop. And also, when the concentration of the alcohol reaches 14%, fermentation stops. And at this point, the alcohol kills the yeast. So what are alcohols used for? So for example, let's look at ethanol. Ethanol is very often used in alcoholic drinks. Not only in alcoholic drinks, but it can also be used in perfumes. And if you mix ethanol with different hops, barley and water, you can produce a large variety of alcoholic drinks, like beers. In order to get spirits, you have to distill. And by doing the distillation you will get a higher percentage of alcohol. We can also use ethanol as a fuel, and in petrol ethanol can make up to 10%, and this gives it a higher octane rating, meaning that it burns more efficiently. And also ethanol comes from a renewable source, therefore when we add ethanol to petrol, the petrol becomes more environmentally friendly. We can also use ethanol in methylated spirits, and these are a mixture of ethanol and methanol with some dye added. But because of this it makes it toxic, and therefore it's exempt from tax. Therefore it's much cheaper. However, it's very dangerous, and even a small amount can cause severe organ damage and even death. And it's mostly used as a good hydrocarbon solvent. What about methanol? Well, methanol can be used as a high-performance clean burning fuel, and also it is often used in feedstock for the chemical industry. So let's now look at the reactions of alcohols. So the first reaction is combustion of alcohols, and combustion of alcohol happens if there is a plentiful supply of oxygen. So the alcohols will burn to form carbon dioxide and water. So for example, we have ethanol plus O2 producing CO2 and H2O. We can also have this write out the equation for methanol and oxygen, propanol or butanol. The important thing with combustion of alcohols is always to balance it correctly. This alcohol's reacting with sodium. So if you drop a small piece of sodium into ethanol, it reacts quite steadily to give off bubbles of hydrogen gas, and it will leave a colorless solution of sodium ethoxide. And sodium ethoxide is known as an alkoxide. And then if you evaporate the solution further, a white solid will be left, which is sodium ethoxide. So this is the equation. So we have sodium solid reacting with ethanol liquid to produce sodium ethoxide, which is C2H5ONa, and to produce hydrogen gas. So why do we need this reaction? Well, there are two reasons. The first one is to dispose of small amounts of sodium safely. And this is because if, let's say, we had some small amount of sodium left and we wanted to, I don't know, put it down the drain, the reaction with sodium and water is very, very vigorous and violent. Therefore, we can first react the sodium with a bit of ethanol, and then once it is dissolved, we can then put it down the drain, and it is safe to do so. We can also use this reaction to test for the OH group in alcohols. However, it is quite dangerous because obviously sodium is quite reactive, so it's not the best test for an alcohol. So also sodium reacts violently with acids to produce a salt and hydrogen, so you would first have to be sure that the liquid you were testing was neutral. Let's look at oxidation of alcohols. So oxidation of alcohols can produce aldehyde, ketones or carboxylic acids. And by oxidizing alcohols, we can then establish whether we have a primary, secondary or a tertiary alcohol. So in order to oxidize alcohols, we use acidified potassium dichromate. And generally this is orange in color, and is a mixture of sulfuric acid, H2SO4, and potassium dichromate, K2Cr2O7. And the orange color is due to the chromium 6+ ions in the potassium dichromate. So if it is oxidized, the Cr6+ ions become reduced, so then the solution will turn green. And the green color is due to the Cr3+ ions being present. So if we use this test, the results will only show primary and secondary alcohols. And tertiary, because they can't be oxidized, there will be no color change. And we'll now discuss in more detail what happens with the 3 types of alcohols when they get oxidized. So let's first look at oxidation of primary alcohols. So primary alcohols can form 2 products. So let's first consider the first stage. So in the first step, primary alcohol will oxidize to an aldehyde. So first of all, we need to gently heat the primary alcohol with acidified potassium dichromate to make an aldehyde. So for example, in this equation here, we have propan-1-ol with O in square brackets. Again, it represents the oxidizing agent, and the product will be propanal plus H2O. So we can just, I've circled this here to show where the water would come from. So 1H from the OH group, and also 1H from the carbon to where the OH group is attached, and some will come from the oxidizing agent. And this will produce a double bonded oxygen with a hydrogen left over. And this is the apparatus that we would use to oxidize primary alcohols. And if we just want to produce the aldehyde, then we can distill off the aldehyde, like shown here, into this test tube by cooling it. And we use this apparatus here where we have cold water coming in, cooling this tube, and then coming out again. However, if we want to produce a further product, we can leave the aldehyde in the mixture, and primary alcohol goes to aldehyde, and then if we leave it inside, it will then go to a carboxylic acid. So again, we would need to heat it with excess acidified potassium dichromate, and then it will be completely oxidized, passing through the aldehyde stage to form carboxylic acid. So again, we have propan-1-ol reacting with an oxidizing agent under reflux to produce propanoic acid. And so this carbon with the double bonded oxygen and the OH group is sort of the general group to look out for that tells us that this is a carboxylic acid. This is done under reflux. So refluxing allows you to heat, boil volatile liquids for a long time. The condenser stops the volatile liquid from evaporating off. So this is what a reflux apparatus looks like. So, and when we make carboxylic acids, the mixture is refluxed. We don't need to worry about the oxidizing the aldehyde, as we need to do this in order to reach the carboxylic acid. So again, the distillation evaporates and condenses liquids at different temperatures, and it collects the liquid you want around the boiling point and discards any other. So again, this is how we would collect the carboxylic acid. Oxidation of secondary and tertiary alcohols. So secondary alcohols can be also oxidized by acidified potassium dichromate. However, notice that the OH is removed with a hydrogen on that carbon, leaving the carbon-oxygen double bond. So I've shown it here on the example of propantuol. So again, it takes one hydrogen from the OH group and one hydrogen which is directly attached to this carbon which carries the OH group to produce propanone, and propanone is a ketone, and also water is produced. So this is the oxidation of secondary alcohols to produce a ketone. Tertiary alcohols, although they have an OH group, they do not oxidize. And let's just look on the next slide why this is. So why do tertiary alcohols not undergo oxidation by potassium dichromate? Well, if we look at primary, secondary and tertiary to compare them, we can see that in primary alcohols the oxidizing agent is removing the hydrogen from the OH group and the hydrogen from the carbon which is carrying the OH group. Secondary alcohols, the same thing can happen, that because the carbon has this lone hydrogen, that oxidation can take place. However, in a tertiary alcohol, if we look, it's got 3 methyl groups around it, and there are no hydrogens attached to this carbon that is carrying the OH group, therefore it cannot be oxidized. So how can we use oxidation of alcohols to test what type of alcohol we have? Well, so first of all, we need to test for the OH group. So we need to show that we have a neutral liquid, free of water, and that it's reacted with solid phosphorus chloride to produce a burst of acidic steam, which is hydrogen chloride fumes. Then we would add a few drops of the alcohol to a test tube containing potassium dichromate solution, which is acidified with dilute sulfuric acid. And we gently warm the tube in a water bath. And after heating, we can then use a Tollens or Feeling or Benedict solution. And depending on whether we have an aldehyde or a ketone, we will have a different outcome. So again, if we have a primary or secondary, there will be a color change to green. And when we have a tertiary, there is no color change because we know that tertiary alcohols don't oxidize. We can also use Schiff's reagent, which is quite a bright pink-purple dye, and it becomes decolorized when we pass sulfur dioxide through it. So in the presence of even a small amount of an aldehyde, it will turn bright magenta. And if there is no color change, then no aldehyde, and therefore we don't have a primary alcohol. So this is another test we can use. So let's just do a quick overview of oxidation of alcohols. So again, as mentioned before, the O in square brackets represents an oxidizing agent. As we know, primary alcohols first go to aldehydes, and then if they're left to oxidize further, they will become carboxylic acids. Secondary alcohols only oxidize to ketones, and tertiary alcohols, there is no reaction. So again, this is a primary alcohol because the carbon that has the OH group only has one other alkyl group attached to it. First of all, it will oxidize to propanal, which is an aldehyde, and we know that this is an aldehyde because we have the carbon-oxygen double bond and one hydrogen. And then if we leave it further, it will become propanoic acid, which is a carboxylic acid, and we know that this is a carboxylic acid because we have the carbon-oxygen double bond, and also on the same carbon we have an OH group. For secondary alcohols, and this is a secondary alcohol because the carbon that carries the OH group has 2 methyl groups attached to it. So when we oxidize a secondary alcohol, the product is a ketone, in this case propanone, and no further oxidation takes place. And this is a tertiary alcohol, and this is tertiary because the OH group is attached to the carbon that has 1, 2, 3 methyl groups. and because it does not have any lone hydrogens attached to this carbon, no reaction or oxidation can take place. Let's now consider dehydration of alcohols, and when we carry out a dehydration reaction, we go from an alcohol to an alkene, and alkenes, as we know, have double bonds. This is also known as an elimination reaction because we are eliminating the H2O from the alcohol. So for example, we have ethanol here, and if we heat it with concentrated H2SO4, we will the product will be ethene with water. And the red, we've highlighted the red OH group and the hydrogen to represent this OH group, and this hydrogen will form the water. And as a result, the carbon-carbon double bond will form. The catalyst, as mentioned, is usually concentrated phosphoric acid or concentrated sulfuric acid. And again, you heat it under reflux and then distill it. You can do the same thing for cyclohexanol. And cyclohexanol, if we remember, cyclo meaning that there is a ring structure, hex meaning there is 1, 2, 3, 4, 5, 6 carbon atoms, and ol meaning that there is an OH group attached somewhere. Dehydration again will happen if we use a catalyst. In this case, we can use concentrated phosphoric acid to produce a cyclohexene and H2O, and it's hexene now because there is a double bond, therefore it's an alkene, and again water is produced. So let's now look at substitution reactions that alcohols undergo to form halogenoalkanes, and this is also known as halogenation. So the general reaction looks like this, where we have the ROH. OH represents that this is an alcohol, plus HX, meaning that we are reacting this alcohol with a hydrogen halide. X is the halogen, so chlorine, bromine, or iodine, and the product will be RX plus H2O. So let's look first at the reaction with hydrogen chloride. So primary and secondary alcohols react very slowly with hydrogen chloride, so it's not very interesting. Tertiary alcohols react rapidly if you shake them with concentrated hydrochloric acid at room temperature, and this is what the reaction looks like. So here we have a tertiary alcohol reacting with hydrogen chloride, and we've highlighted the Cl in red to show where it's attaching. So it's attaching itself, it's eliminating the OH group and attaching itself where the OH group used to be, and the OH is then leaving to produce H2O. One of the hydrogens in the water will come from the OH group, and one hydrogen will come from the HCl to produce water. So let's look at replacing of the OH group with bromine, also known as bromination. So first of all, you treat the alcohol with a mix of either sodium or potassium bromide, and with 50% sulfuric acid. So in this case, we have potassium bromide reacting with sulfuric acid to give us a hydrogen bromide, which we then can use to react with the alcohol. We then warm the mixture and carry out distillation, and we will distill a bromoalkane. So again, we have ethanol here reacting with hydrogen bromide to produce bromoethane and water. So what about a reaction where the OH group is replaced by iodine? This is also referred to as iodination. Again, the alcohol is reacted with a mixture of either sodium or potassium iodide and concentrated phosphoric acid. And then we distill the iodoalkane. There are two ways. So either we can use hydrogen iodide from this reaction to react it with the alcohol, or we can use phosphorus with iodine to first produce phosphorus triiodide. Triiodide meaning that there's one phosphorus and three iodides, and this will the Pi3 will then react with the alcohol to give us the same product as this reaction. So there are two different ways of carrying out halogenation of alcohols. So let's look at the reaction of alcohols with PCl5 and how we use this reaction as a test for the OH group. So alcohols react with liquid phosphorus trichloride to make chloroalkanes, as shown here, PCl3, and the product is a chloroalkane. Also, we can also carry out chlorination using solid phosphorus chloride or phosphorus pentachloride. But this reaction is very violent, and this happens at room temperature, and it produces clouds of hydrogen chloride gas. And we use this as a test for the OH group. The hydrogen chloride, we can use this with damp litmus paper. However, for this reaction to happen, we need to make sure that it's neutral and that there is no water present, because otherwise the PCl5 will also react with water and we will have a mixture of products. So here in the center we have ROH, which is the general way to represent an alcohol. So first of all, it can undergo combustion, and this happens when we have alcohol reacting with oxygen and the products are carbon dioxide and water. Another reaction of alcohols is with sodium. So when we add sodium, the product is RONA plus hydrogen gas. We also know that alcohols undergo oxidation reactions, but it depends whether how and what will be produced, whether it's a primary, secondary, or tertiary alcohol. So if a primary alcohol is oxidized, it will first produce an aldehyde. And if we leave it to oxidize further, a carboxylic acid will be produced. A secondary alcohol is oxidized to a ketone, and this is the final product. There's no further oxidation. And tertiary alcohols do not undergo oxidation reactions. And the oxidizing agent for all these reactions is K2Cr2O7 in H2SO4, so it's acidified. Another reaction that alcohols undergo are dehydration reactions, and this is when we heat an alcohol in concentrated H2SO4, and the product is an alkene and water. So this is a useful way of producing alkenes from alcohols. Alcohols also undergo chlorination, bromination, and iodination, and this is when the OH group is replaced by a halogen. So the general formula for this reaction is ROH reacting with HX, where X is the halogen, to produce RX with H2O. So for chlorination of an alcohol, we usually add HCl or PCl5. For bromination, we use hydrogen bromide, and for iodination, we can either use PI3 or hydrogen iodide.